So nitrogen gas. Nitrogen is in group 15 of the periodic table. Non-metallic nitrogen gas makes up 78% of Earth's atmosphere. Where diatomic molecules, all previous information, not prerequisite. We know it's unreactive because of the triple bond. We do understand that it's triply bonded covalent molecule, a small molecule with a lot of bond energy required to break that bond. So since the triple bond is very strong and the bond energy is almost 1000 kilojoules per mole, the bond is difficult to break. This is not the exact value is a little less than 1000 kilojoules per mole. This is the approximate value that I've quoted over here for your understanding. So this bond is difficult to break and it will only react under extreme conditions. For example, I have discussed the example of nitrogen and oxygen reacting together during thunderstorms and nearby the lightning area where there is enough energy that is gained by both nitrogen and oxygen molecules to have the activation energy, the necessary energy required by the reaction to occur. So since I've given that example many times along with the reaction as well, nitrogen and oxygen are converted into nitrogen oxide. So upon further oxidation, this is converted into from nitrogen oxide to nitrogen dioxide, or that is nitrogen 4 oxide. 2 and 4 oxide are the proper IUPAC names for the differentiation. So we do understand this can be further oxidized in the presence of water, and that actually happens naturally during the rainfall, which actually converts the nitrogen dioxide into nitric acid, becoming the one of the biggest cause of acid rain on the planet. Now you can see the reaction nitrogen dioxide, and then with water, then there is oxygen, which is converting it into nitric acid. Now the sequence of reactions in the atmosphere forms part of the natural nitrogen cycle. In this way, nitrogen from unreactive insoluble nitrogen gas actually becomes a part of the soil. Though it turns the soil acidic, but we do understand that it turns the soil acidic by going with a simple reaction, giving away the H positive ion and the nitrate ion. Now, if we talk about these nitrate ions in specific, which he did over here, it says that they're soluble, plants can take up, and plants can actually use the nitrate ions to make proteins, since that's the major part of the proteins plant form for their usage. Now, this is actually the way the food is made for plants themselves. Actually, it would be good if we say the food for the entire planet. So it is essential for the healthy growth of plants. We specifically mentioned this sentence because we have discussed this sentence as a part of IGCSE. As a prerequisite, the examiners expect the students to know that the healthy growth actually require the root part, the shoot, or which we call the main branch part, and of course the leaf parts. Their formation, when a new plant grows into a well-grown plant, their formation is required, and their formation completely depends upon the cells being converted or multiplied. Of course, that is going to require a lot of protein, and that protein comes from usually the nitrate ions. And don't forget one more requisite. We have been talking about that there is a little bit of scarcity in the different parts of the world where there is not enough food for the plants. That's why we're coming up with the usage of artificial fertilizers. And among artificial fertilizers, the nitrogen-based ion, which is most common and famous, are the ammonium ions. So if I truly talk about the way the plants form proteins, from the two most common ions that is fed into the soil, that would be ammonium ion and that would be nitrate ion. These both are soluble. These both can be taken up by the plant roots, and these both can be converted into proteins. So this gives the idea of many prerequisites that we have done previously in IGCSE. So moving forward, while we are talking about ammonia mines, we may discuss ammonia and ammonia mines as well. The ammonia NH3, the gas, is an important compound of nitrogen. It is the only common alkaline gas. All the gases that you come across with, and especially the gases that you test or have tested back in IGCSE, and if I actually name them, that would be hydrogen, that would be oxygen, that would be uh, not nitrogen actually, that would be SO2, that would be Cl2, that would be CO2. We have been using and testing these gases all along. So apart from all of them, this is the only alkaline gas. We do understand these are acidic gases, right? And if I be true, these are neither acidic nor alkaline. Well, I can't exactly call them neutral, but these are not neither acidic nor alkaline. So you know that among all the gases that you have tested back in IGCSE, this one was the only one that was alkaline. That's why he's saying putting it in like that. And if I say the word alkaline, of course, I hope you do understand the red litmus paper would be turned to blue. Now, Hibbert process is the process that we use to form ammonia. If I talk about the structure of ammonia, you already know about the lone pair, the bonded pairs, and you also know that ammonia is capable of getting actually donating its own lone pair for uh, accepting an H positive ion from an acid. This is a dative bond. As soon as you see a structure like this, straight line, straight line, straight line, covalent bonds, arrowed line, dative bond. This plus sign is actually coming from this hydrogen as H positive from the acid. So that's why ammonia can act like a base if we talk about proton acceptors. So the positive charge on the ammonium ion formed is spread over the whole ammonium ion. That's why we use the bracket. This charge is not concentrated on the hydrogen ion. They accepted the lone pair of electrons. Chemists have found that all the NH4 bonds in NH4 positive are the same length. Even the dative bond is actually of the same length as the covalent bond. This is the evidence that all four covalent bonds in NH4 positive are equivalent and positive charges evenly spread around the whole ion, hence the use of brackets. Now, this specific paragraph, this whole paragraph, you should memorize this paragraph. We have dealt like 5 to 6 different MCQs about it already in the bonding chapter. We are going to deal with more MCQs like this in this chapter number 13. So moving on, basicity of ammonia. When we use the word basicity, it's all about the acceptance of the proton. So the easily a substance can accept proton, the more basic it is considered to be. So let's go ahead and find out the basicity and let's compare it with a few more elements as a part of A-level syllabus. So not elements, substances actually. Basicity of ammonia. When ammonia donates its lone pair to an H positive ion, ammonium ion is formed. Ammonia acts as a base. So if we talk about the base over here, this is actually frosted Lowry base accepting a proton. Ammonia is an example of weak base. In aqueous solution of ammonia, equilibrium mixture is established. This is already an equation that we have discussed before. This reversible reaction sign means an equilibrium would be established. And of course, all laws that apply to an equilibria as per the Chatelier principle will also be applicable over here, which means adding more water would take it into forward direction and adding more aqueous ions, alkaline ions with negative will take it into reverse direction. Now, talking about this equilibrium in specific, the position of equilibrium lies well over to the left. This means only a few portions of NH3 and water actually act as a base and acid respectively to form ammonium ion and hydroxyl ions. So the concentration of ammonia is always greater than the concentration of ammonium ions or the hydroxide ions. This makes ammonia solution only weakly alkaline, unlike a strong base such as sodium hydroxide or potassium hydroxide, which dissociates completely, hence the word strong base. So if we heat an ammonium salt with the base, what happens that the ammonium ions produce ammonia gas. Along with that, it produces water and of course a salt. This reaction is also a prerequisite from IGCSE. We've studied this reaction before. Ammonium ions plus an alkali gives a salt plus water plus ammonia. And this ammonia can always be tested. A temperate litmus paper will turn to blue. And the same reaction is given in the diagram, that is, it is being tested with the litmus paper. So it gives us the idea that ammonia gas has been produced from the ammonium ions. So we can use the acid-base reaction of ammonium salt with the base as the basis of test for ammonium ions. If an unknown compound containing ammonia binds, it will give off ammonia when heated with the base, and this gives a pretty good idea of probably the positive ions of the substance. Moving on, nitrogen oxides in the atmosphere. Now, before I move any further, something that we have done as a prerequisite, I'm going to talk about chapter number 7. I'm going to talk about oxidation reduction states. Since you can see nitrogen 2 oxide, nitrogen 4 oxide, I hope you understand that 2 oxide or 4 oxide or 3 oxide or 5 oxide, these have been discussed before. Even 1 oxide has also been discussed as examples. Okay, so nitrogen is capable of bonding with oxygen in many different ways. So if you get the point of many different oxidation states which nonmetals are capable of, the point I was trying to make has been achieved. Now, a simple oxidation of nitrogen takes place in this kind of reaction. So this also happens under high temperature inside car engines, something we studied back in IGCSE. It was a very important MCQ. If you have practice, you must know that this was considered for paper 2 as well as paper 4 back in IGCSE for both theory and the MCQ papers. Since we usually use fuels in compressed form, we ignite them under spark. That's mainly the air-fuel mixture, nitrogen, oxygen, and the fuel. Under high pressure, high temperature, nitrogen can form nitrogen oxides. These oxides of nitrogen are then released into the air through car exhaust fumes. They pollute our atmosphere. They cause acid rain. They cause smog, something we have discussed in previous chapters as well as in IGCSE. If I discuss acid rain in specific, I hope you do understand the formation of NO leads to the formation of NO2, which later on leads to the formation of HNO3. This is oxidation as well as oxidation in presence of water. Now, rainwater droplets, tiny droplets that make up clouds, these droplets get larger as temperature drops. When heavy enough, these droplets containing nitric acid will fall as acid rain. Now, dilute sulfuric acid is also found in acid rain. This also comes from another pollutant, sulfur dioxide gas. Now, we do understand that sulfur dioxide gas is another non-metallic based gas, non-metallic oxide, which is capable of getting further oxidized. So we do understand this can produce SO3, and this can be converted into SO3 and later on into sulfuric acid. Since we're talking about sulfuric acid, nitrogen oxides cause acid rain directly. They also act as a catalyst in the reactions that make dilute sulfuric acid in the atmosphere. NO, NO2, both can catalyze the oxidation of sulfur dioxide, SO2, during the formation of acid rain. This is then converted into SO3. Take a look at the reaction. SO2 plus NO2 gives us SO3 plus NO. This reaction is actually catalyzed by the nitrogen oxides themselves. So the NO2 is regenerated when NO reacts with oxygen in the air. So there is further NO2 produced. That's why we were talking about it as a catalyst. So it keeps on actually oxidizing SO2 into further SO3. This SO3 upon addition of water is then converted into H2SO4. So the process keeps going on, and the nitrogen oxide keeps catalyzing the whole process. So this is more like a cyclic process. The NO2 molecule can go on oxidize sulfur dioxide, moving on SO3, moving on H2SO4. So we have dilute sulfuric acid as a part of acid rain as well. So this is actually a big problem. If I talk about photochemical smog, we're going to come to the remedies, but first of all, the problems themselves. So photochemical smogs are also a part of the reason for this photochemical smog is NOx or oxides of nitrogen. Now, these pollutants, which react to make other pollutants in the atmosphere, are commonly known as secondary pollutants. This is because they're not given off directly from human activity. For example, they're not vehicle exhaust gases or gases for power plants. Nitrogen oxides are the example of primary pollutants. They're given off directly into the air by the source of pollution. Primary pollutants in exhaust fumes are also volatile organic compounds. Unburnt hydrocarbons, sometimes from the fuel. This usually happens through the leakages and other problems like that. So the oxidized products also can be a problem. VOCs or volatile organic compounds can react in sunlight with oxides of nitrogen to form peroxyacetyl nitrate. We have been abbreviating it as PAN previously. We discussed back in IGCSE that PAN is an important secondary pollutant. We are quoting the same thing over here. Chemical formula can be this. This seems a bit difficult to talk about CO3. If it was CO2, something in between, you would probably understand we are talking about something like this, but CO3 is something different. Well, moving on, it's not the structure we need to focus on right here because that's not a part of AS. So I'll keep moving on. And sunlight provides energy needed to start off the reactions in the atmosphere. So we call them photochemical reactions and photochemical smog, as you can see. So the word smog is actually a combination of smoke and fog. Smog is now a big problem around the planet. So PAN is one of the harmful pollutants found in photochemical smog. There are many harmful pollutants in photochemical smog. PAN actually affects lungs and eyes, and in a high concentration, it also affects plant life. Apart from affecting the lungs and eyes of normal humans, the ones those are already suffering for asthma, PAN is actually a real bad news for them. PAN is more like a poison to them. So reducing the effect of nitrogen oxide, car exhaust systems are now fitted with catalytic converters. It actually helps to reduce the pollutants. Catalytic converters functioning was defined back in IGCSE, and I love those lines. Those lines are very good, that they actually convert more harmful gases to less harmful ones, or we can say harmless ones, since it's also mentioned over here. So that's the way it works. Now, carbon monoxide is directly toxic. NO is a big problem. It actually leads toward acid rain. It leads toward photochemical smog. It leads toward catalytic activity of formation of many primary and secondary pollutants. So it's a big problem. But it is converted into carbon dioxide and nitrogen. Though carbon dioxide and nitrogen seemingly are harmless, but let me tell you, nitrogen may be a part of oxygen and is harmless. Carbon dioxide is definitely now one of the greenhouse gases. So we don't exactly write them into harmless gases. If he's using the word harmless, it's specifically using it for nitrogen gas. We never use the word harmless for carbon dioxide. Carbon dioxide is still catered as a greenhouse gas and still considered as a problematic gas, not because of its nature, because of its amount on the planet Earth. So it actually leads to bigger problems. And I guess, yeah.